Hi all, this is lecture 16 of engineering mathematics from the University of Notre Dame. So we will finish today the discussion about determinants and some related terminology. So let me go back to reviewing some of the fundamental things we have seen for 2x2 and 3x3 determinants, and then we will try to generalize. All right, so we have seen that a determinant that is of a matrix that is 2x2 has two terms. Two terms you can think 2 factorial, and these two terms come with plus and minus signs. In general, an n by n determinant has n factorial terms. Half of them are with a plus sign, the other half are with a minus sign. So, for example, if you look at the determinant for a 3x3 matrix, it has 6 terms. 3 of them are with a positive sign, and 3 of them are with a negative sign. And I'm indicating here 2 of the terms, one coming with a positive sign, and another one coming with a negative sign. We will see this again extensively with more details. So here I'm just summarizing some of the facts. So we know exactly what we need to cover in detail in the lecture today. So the thing I want to state right away is that in these 6 terms that you get for a 3x3 determinant, in every term, every row and every column appears only once. This is fundamental. So once a row is taken, a column is taken, you have to move to the remaining rows and columns to see what terms you can combine together to get something like this term or this term with a negative sign. Now, you may wonder why do you have a negative sign here. So if you can see, the first term is in row 1, column 3. This is row 2, column 2, and this is row 3, column 1. So you can immediately see that to get this term, you have to have an exchange between columns 1 and 3. So the columns here that you get is 3, 2, 1, and you need to have one exchange to go back to 1, 2, 3. And if you have one exchange, that's a minus sign. If you have 2 exchanges, it's minus sign square, so that's a plus sign. So again, every row and every column in each term appears only once. And the signs have to do with the number of exchanges that you need to do in the order of the columns in each of these terms that is required to go back to the arrangement of the columns 1 to 3 of the identity matrix. So if we look again at the 3x3 matrix, and 2 of the terms that involve A11 look like this. So if you put the 2 terms outside inside the parenthesis multiplied by A11, this term inside the parenthesis is what we call the cofactor of cofactor C11. Okay, so it's the cofactor that corresponds to the element of the matrix A11, and we will see how these cofactors again are coming in the calculations for computing determinants. But let me just state the general result. If you want to, so this is 2 of the 6 terms that you get in a 3x3 determinant. So if you want to write the determinant for an n by n matrix, it looks similar, where you effectively expand in the first row of the matrix, so A11, A12, A1n, and each of these terms is multiplied with the corresponding cofactor. And right now, the only thing I'm going to state is that each of these cofactors is a smaller determinant of size n minus 1. And the other thing I will state is that this expansion that we have done here on the first row, you can do exactly the same identical expansion on the second row or the nth row, and also you can do the same expansion for each column of the matrix A. So this is a very powerful result. Now, you remember we discussed on how to compute the determinant from the pivots after you do an LU factorization. So let me just remind you the end result. So if you don't do any row exchanges and you factorize the matrix, effectively the determinant of A is the determinant of L. And as a reminder, L has ones in the diagonal, so the determinant of that is equal to 1. And the determinant of U is the product of the pivot elements. Actually, these commas here should not be there. These commas should simply be multiplication. Okay, so this is if you don't have any row exchanges. If you actually have row exchanges, you can apply the same formula that you see here, but instead of applying it to A equal LU, you're applying this to P, where P is accounts permutation basically of the rows that you have to do on A, and row exchanges, and so PA equal LU. And the determinant of P, as we know, is going to be plus or minus 1. So effectively, the result is going to be the product of the pivots in the factorization of A times plus or minus 1, depending if you have done any row exchanges or not. Okay, so let me do a simple example. This is a 3 by 3 matrix. You can see here this element is 0, so that's not good. So the way we proceed is we do a row exchange. We take row 3 and we put it as row 1, and row 1 goes back to row 3. And here you actually don't have to do any further factorization to compute the determinant, because you can immediately see that this matrix is already in an upper triangular form. So the determinant of this matrix is going to be the product of the pivots, which is 4 times 2 times 1, but also a minus 1 sign because we have done one row exchange. Okay, so it's very simple, no algebra necessary. The product of the pivots times the determinant of the permutation matrix that accounts for the row exchanges that you had to work on. Okay, let's do another example. So in this example, it's a little bit more complicated, so most probably you will have to do this with MATLAB if you want to do it faster. So this is a very standard 3-diagonal matrix, actually very common structure that appears in many problems in finite differences and finite elements. And what you see here is the LU factorization, and notice the L matrix again has ones in the diagonal and only has one line of elements below the diagonal, and U again is an upper triangular with only one line of elements above the diagonal elements. So we can go in and compute directly the determinant of this matrix A, of this 3-diagonal matrix, by multiplying the pivots. And you can see you multiply 2 by 3/2, so the 2's are cancelled. Then you multiply 3 by 4/3, the 3's cancel, and eventually what you get is this very important result that the determinant for this 3-diagonal matrix is equal to n plus 1. So you can actually realize here that in computing, when you take the product, let's say, of the first two pivots, 2 and 3/2, really this is the determinant of this first 2 by 2 matrix. And generally, when you take the product of k pivots, that's the determinant of a k by k matrix starting from the top left. And so generally, the determinant of any piece of this matrix that you cut that is k by k, the determinant of it is d1 to dk, where you only take the first k pivots. So in general, if I can just go directly to the equation on at the end of the slide, if you want to identify the kth pivot dk in terms of the determinants, literally it's nothing else but the determinant of the k by k matrix divided by the determinant of the k minus 1 times k minus 1 matrix. Again, always defining these matrices starting from the top left. Okay, so this is a very nice way to actually see the pivot elements being nothing else but a ratio of determinants. All right, we are going to, I notice here we are assuming obviously that none of these determinants is 0. Otherwise, we are going to have difficulty to apply this formula and compute in a valid way the pivot element. Okay, so what we need to do now is introduce the big formula for determinants and something that we can apply to any sort of a matrix and see what the underlying structure is. So let me just briefly remind you what is the 2 by 2 determinant. Okay, so this is what you know from your earlier classes. Okay, we will see, we will revisit sort of how these two terms with a plus and minus sign come together and how we can define this from the fundamental properties of the determinants. But this is what you are accustomed to use for a 2 by 2 determinant. And similarly, if I remind you the 3 by 3 determinant again, you may have been able to write the 3 by 3 determinant as an expansion on using the elements of the first row of the matrix. You see here A11, actually it's the first column, right? It's a little bit different from before. So we expand on the first column. And these determinants, including the signs, are what we called before the cofactors, right? So we expand this determinant in the first column using the cofactors corresponding to elements 1, 1, 2, 1, and 3, 1. If you put all of these things together, the 3 by 3 determinant with all 6 terms looks like what you have on this on the bottom of the slide. And as a reminder again, and you can please go ahead and test it, every term that you see in this expansion involves every row and every column only once. Okay, so this is a very good way to figure out how these 6 terms are coming in, right? So if you go in the first row, you can select the first column, you can select the second column, or you can select the third column. Then when you move to the second row, you have only 2 choices of column because one of them is taken from row 1. And when you move to row 3, there is only 1 choice of column because you already have taken 2 of the other columns. And this is how you get the 6 different terms that you see here. And the signs, as I mentioned before, have to do with the number of permutations that you need to do to go back to columns 1, 2, and 3 from the identity matrix. Right, so let's see how these formulas are being derived in some elementary way. So what I'm going to do is I'm going to start with a 2 by 2 matrix. And actually, let me go directly so we can save us some time directly on the determinant of this 2 by 2 matrix. So what I'm going to do is I'm going to use the linearity in the first row and split this determinant in the sum of 2 by 2 determinants, where AB is split into A0 plus 0B. And then for each of these determinants, I am going to do the same thing by using the linearity in the second row and split each of these determinants in 2 pieces. So what you see here is the C and D was split in C0 and 0D, right? A0 remains unchanged, and similarly 0B remains unchanged on the last 2 terms. And then I'm splitting CD to C0 and 0D again. All right, the first determinant is 0 because 1 column is 0. The fourth determinant is 0 because 1 column is 0. And effectively what you're actually getting is you're getting this 2 factorial total number of determinants that we have seen before. Okay, and so now we need to evaluate the second determinant that you see here, and we need to evaluate the third determinant that look obvious, but let's do that using the fundamental laws that we have discussed up to now in our lectures. So what I can do is, if I on the first determinant, if I move A out using one of the fundamental, I think it was rule 3A from determinants, and I can move D out. So I have AD times the identity matrix, and actually what you can do, you can I mean, you can look at this in many ways. So one of the ways is to do an exchange of columns. So that will change the sign by -1. And then B and C go in the diagonal, and you can pull them out, all right? And if you pull them out, you're going to get a determinant that is minus B times C. But the way I have written here, this is equivalently as C times B times this permutation matrix 0, 1, 1, 0 that basically permutes columns 1 and 2. So basically, the determinant of this matrix is minus 1. You will need on the first row you use as you can see here, you use column 1, and on the second row you use column. I'm sorry, on the first row you use column 2. On the second row you use column 1. So you need one exchange to go back to the identity matrix. Okay, so that exchange leads to the minus sign that you see here. So again, this is the well-known result that you have seen before, so nothing surprising here. And we can do exactly the same thing for a 3x3 determinant. So for a 3x3 determinant, you can, if we can go directly to the results, you can, if you split this, you will get many terms that they are 0, but effectively at the end of the day, the non-zero terms are these 6 terms that you see here. And you can verify that every term uses each row and each column 1. So for example, if I look at the second determinant, in the term that results from the second determinant, first, in this element A12 uses row 1 and column 2. This uses row 2 and column 1, and this uses row 3 and column 3. So what is important, let me just go back again. Let's concentrate on the third determinant. You notice on row 1, I use column 1. On row 2, I use, on row 1, I use column 3. On row 2, I use column 1. And on row 3, I use column 2. So basically, the sequence of columns that I have on this third term, written here in boldface, all right, on this term, is 3, 1, 2. Okay, so can somebody guess actually what will be the sign for this particular term? How many exchanges do I need to go back to 1 to 3? I mean, how are you going to get the sequence 3, 1, 2 starting from 1 to 3? So you can actually think, one of the things you can do is from 1 to 3, you can exchange columns, you can exchange columns 1 and 3. So from 1 to 3, you can go to 3, 2, 1. And then on that, you can exchange 1 and 2. So from 3, 2, 1, you can get 3, 1, 2. So you have 2 column exchanges, which means actually the sign of this term is going to be a plus because it's going to be -1 squared. Okay, so this is, I think I'm indicating these details for those who are interested on this slide. Okay, so again, I am indicating for each of these terms that you see here the column numbers, and you see for the term we just discussed, the sequence is 3, 1, 2. All right. Again, row 1 uses column 3, row 2 uses column 1, and row 3 uses column 2, 3, 1, 2. And the details on the permutations that you need to go to 3, 1, 2, starting from 1 to 3 or in reverse, is basically to do an exchange of columns 1 and 3. Right? You can see here from 1 to 3 I go to 3, 2, 1, so I don't touch column 2, and then I do an exchange of columns 2 and 1 to get 3, 1, 2. So 2 exchanges, so A13 times A21, A32, this determinant here of this permutation matrix is going to be equal to 1. So half of these terms, the first 3 actually, they're going to give me a plus sign, and the 3 terms on the bottom are going to give me a negative sign. And we can see actually, if we concentrate on the 4th term, you notice on row 1 I have column 1, on row 2 I have column 3, all right? Column 3, and on row 3 I have column 2. So basically it requires this only one exchange of columns 2 and 3, and I'm indicating this above the determinant in this schematic. So if there's only one column exchange, that's a sign of -1, and that's how you get 3 positive signs and 3 negative signs. All right, so let me write a very general formula now. So you remember we said that from every row you pick up one column, you keep track of which rows and columns have been taken as you move down to another row and another column. So effectively, on row 1 you pick up some column alpha, on row 2 you pick up some column beta, not alpha of course, and then of course on row n you pick up whatever last column is left that I call here omega. So effectively you can think of the determinant being nothing else but the product of all of these terms for all possible permutations of the indices 1, 2 to n, and you multiply each of these terms with the determinant of the permutations that you have performed to go from 1, 2 to n to the indices alpha, beta, omega. Okay, this is again how in the 3x3 cases we get 3 terms plus and 3 terms with a negative sign. This is really the big formula, and all all different formulas that we are going to discuss today really come from this major big formula. So this is what you really need to remember by taking each row, one row at a time, starting from row 1, and for each of these terms you are using different permutation of the columns by selecting column alpha from row 1 and then column beta for row 2, etc. And then you multiply with the corresponding determinant of the permutation matrix. Okay, so let's do an example. Suppose you have this simple 4x4 matrix and you want to compute the determinant, and you want to do this with as little algebra as possible. So basically the idea here is you have to identify all the non-zero terms where each term uses every row and every column only once. So what I'm going to do is I'm going to use on row 3, I'm going to use the element C. All right, so I'm going to use column 3. On row 1, I'm going to use column 1. On row 2, I'm going to use column 2. And on row 4, I'm going to use column 4. All right. So what, if you look at that, it will give you basically the product of the pivots will be C. So that that term is going to give you a contribution C to the determinant. And then the question, of course, is, are there any other non-zero terms that you can also extract? So when it comes to column 3, you notice you can actually use the element A, you can use the element B, or you can use the element D. So let's do the following thing. let's, on row 2, let's pick up column 3. So we're going to pick up that element B that you see here. Again, on row 2, I'm going to pick up column 3, which is that element B. So if you cross row 2 out, all right, if you cross row 2 out and you cross column 3 out because it's taken in that term, you look at row 3 and you say, okay, what is left in row 3 to use? And you only see zeros because you remember this column is taken, so C's cannot be used anymore. All right, so remember on row 2 I use column 3, so I use this element B, but the whole row and the whole column 3 have been taken. So when I go to row 3, there is nothing, there's no column that will give me an non-zero element, so that term will contribute nothing to the determinant. And you can repeat the same thing by taking, let's say, row 1 and column 3, or you can take, row 4 and column 3. You will see again that the additional terms don't contribute much, and they give you 0. Now, so remember that in this case, because this is a 4x4 determinant, right? So you have a total of 24 terms, but really we don't have to compute any of them because we can reason that all but one term is 0, and that one term has a contribution equal to C. Now, there is another simple way if you want to show that the determinant of this matrix is C, and what actually you can do here, you can envision that you do Gauss-Jordan elimination, and you can. So first, you can get rid you can get rid of D with elimination, and then you can get rid of the things above this pivot element. So you can get rid of B and A. So really, then what you left in the matrix is 1, 1, C and 1. And that has determinant equal to C. So obviously here we are, if you're going to do this elimination, right, we're assuming that C is not 0. If C is 0, I mean, we already know the answer that the determinant of this matrix is equal to 0 because you're going to have one row that is full of zeros. All right. So let me do another example. Let's say that you're interested to compute the determinant of this matrix A, and has lots of zeros, right? And you don't want to write explicitly, all the terms. So let's start with row 1, right? And see what. So in row 1. Really, your only choice to get anything non-zero is to use column 1. Okay, so remember row 1 and column 1 is taken. Let me proceed from row 1. I'm going to proceed to row 4 because row 4 has only one non-zero element. So in row 4, I am going to use the column 3. So remember, row 1, column 2 is taken, row 4, column 3 is taken. So effectively from row 2 and row 3, I have no choice but to use the first column and the fourth column. Okay, every other term that you can think with any other possible combinations of choices, these pairs of rows and columns will give you 0. So the only non-zero term that you get is actually this permutation matrix here that you see. And if you pay close attention to this permutation matrix, on row 1 you have column 2, on row 2 you have column 1, on row 3 you have column 4, and on row 4 you have column 3. So you really need 2 exchanges to get this from 1 to 3, 4. You need to exchange column 2 with 1, and then you need to exchange 3 with 4. So you have -1 square basically. And as a result, the determinant of this matrix P is equal to 1. And effectively, you know immediately then that the only contribution that you get for the determinant of A is from this determinant of this permutation matrix. So the answer is equal to 1. So here, again, we have many terms. We have 4 factorial terms, and we simple selection of the non-zeros, the combinations of rows and columns that give non-zero contribution to the determinant. We conclude that the determinant of this matrix is equal to 1. Okay, so let's go back to this idea of cofactors that we introduced in the early part of the lecture. And so let me just jump directly to slide 56. And so what I'm going to do is I'm going to write down the formulas that I had before. So what we do here is we expand in computing the determinant using the J row of the element A. So these are the corresponding cofactors, and each of these terms is basically computed. So let's say we are looking at the term A J1. Is the CJ1 is defined by removing out row J and column 1. Okay, removing row J and column 1, but then we need to add the plus minus sign, and the general calculation that you have to do is the sign is comes from -1 to a power J plus K when you compute the cofactor CJK. So two things to remember, right? That the cofactor, you compute it as the determinant of the matrix that you produce from A by eliminating row J and column K, times a sign that is really -1 J plus K. This matrix, this determinant that you see here, in linear algebra, people call it the minor, right? Again, it's a determinant of an n-1 by n-1 matrix. And the expansion that I have shown you here is in terms of row J. You can write this in terms of any row of J, but also you can write this as an expansion in terms of the kth column of A, exactly the same result, right? So, and of course, the recommendation here is if you have a big matrix with lots of zeros, you select the row or the column where lots of these alphas will be 0, so you have to do as few calculations as possible. All right, so actually I'm going to bypass a few slides because they summarize these formulas, and let me go to slide 60 to just show you an example in computing a 3x3 determinant using these cofactors. And so in the equation that you see on the top, I'm expanding in the first row. So the first row has elements 1, 3, 0, 1, 3, 0. And for example, the cofactor for the element 1, 1 is, if you eliminate row 1 and column 1, is the matrix 6, 4, 0, 2. And similarly for the element 3 here, the cofactor, you eliminate row 1 and column 2, so you get the determinant 2, 4, -1, 2. And there is -1 sign because you remember to compute the cofactor C1, 2, you multiply by -1 to the power 1 plus 2, which is equal to -1. So the determinant, when you do the algebra, it comes to be -12. And as a verification, you can actually expand on the third column. So you can actually expand on this column 0, 4, 2. And again, you compute the correct cofactors. You have a minus sign on the second term, and the answer obviously comes to be exactly what you expect. So, I mean, this idea with the cofactors is really nothing new, but actually what it is taking the big formula that we derived before, all right? And effectively, when you look at expanding, let's say, on the first row, you take all the terms that A11 multiplies, then you take all the terms that A12 multiplies, and each of these terms is the corresponding cofactor. Okay, so you can, if you want to actually, prove this, you have nothing else to do but to effectively prove that the rules of determinants, basically rules 1, 2, 3a, and 3b, are being satisfied. So I don't think it's worth doing that exercise for this course, and you can find a few more details in the slides. Okay, so the only thing I wanted to show you is this general formula for a 3x3 matrix that shows the cofactors explicitly. And by the way, the cofactors here include also the minus sign. So the minus sign has been accounted inside this parenthesis. So what I wanted to show you is you can take this 3x3 determinant, and if you want to see the cofactors directly, you can envision that you split this determinant using these rules of linearity that we discussed before to these three determinants. And again, because this requires some permutation of columns to compute the determinant, the minus sign that comes in the cofactors is explicitly accounted inside each of these terms. Literally, the bottom line is, right, you can expand on any row, on any column, and the cofactor is plus minus a sign times the determinant of the minor matrix that you get by, in this case, eliminating row 1 and column j, or in general, eliminating row I and column j to find the cofactor Cij. So let me return back to this example. You remember these are three diagonal metrics, and we actually proved with two different methods that, if I remember, the determinant of this matrix, this is a 4x4, but for the general case, the determinant of this matrix, if I recall, was n+1. So if you expand on the first row, so you're going to have 2 times a 3x3 determinant, and then you're going to have minus the minus 1 times, if you get rid of the first row, second column, you have minus 1, and this 2x2 determinant. And actually, in computing this determinant, you notice because you only have one non-zero element, effectively you can expand with the cofactors in the first column, and that involves only a 2x2 determinant. So effectively, to compute a 4x4 determinant, it is 2 times the corresponding 3x3 determinant, okay, minus, I'm assuming if you work the signs correctly here, minus this 2x2 determinant. So actually I can write this in general for an n by n matrix, a three diagonal matrix, as dn equal 2 times dn minus 1 minus dn minus 2. And you can verify, or you can actually use this recursively, starting with 1 by 1 or 2 by 2 matrices. You can verify that the solution to this equation is indeed that the determinant of this n by n 3 diagonal matrix is n+1. So you can see the determinant of n minus 1 will be n, and the determinant of n minus 2 will be n minus 1. So 2n minus n, you get n+1. Okay, so that's another nice way to show, the third way to actually show that the determinant of a 3 diagonal matrix is n+1. Okay, so let me keep moving forward. And so what I'm going to do is I'm going to try to move to slide 66 to discuss a little bit about computing the inverse of a matrix using what's called the Cramer's rule. this is a very inefficient way to compute the inverse of a matrix, but somehow it's a nice exercise on using cofactors and understanding the role of determinant in many linear algebra tasks. So let me first start with computing. Before we talked about the inverse, let me start with computing the solution of a linear system of equations Ax equal to b. So actually what I have done is I have rewritten the problem Ax equal to b on the equation that you see in the middle here in an expanded form. So if you multiply A with the first column, you see you get the first column on the matrix on the right. So the solution of Ax equal to b is already incorporated on this long equation. And if you multiply A with the vector 0, 1, 0, you don't get anything else but the second column of A. And if you multiply A with 0, 0, 1, you don't get anything but the third column of A. So this matrix B1 that you see here is really the matrix B, where the first column has been substituted with the vector B. And remember, I'm interested for now to solve this system of Ax equal b using concepts from determinants. So I have written Ax equal to b with extended algebra in this nice form. So let me do the following interesting calculation. I'm going to take determinants of this of the matrices on the left and the right. So you remember that the product of determinants would be the product of the determinant of A times the determinant of this new matrix. And on the right-hand side, I'm going to have the determinant of B1. Now, would you agree that the determinant of this first matrix by, you notice if you expand on cofactors on the first row, you only have x1. So it's really the determinant of this matrix is x1. So let me take determinants of this equation. So I'm going to have the determinant of A times x1 equal the determinant of B1, which is another 3 by 3 matrix. So x1 is determinant of B1 divided by the determinant of A. So somehow, by forming this matrix B1, where again B1 is the A matrix with the first column substituted with B, I'm able to calculate the first unknown in my linear system of equations Ax equal to b, and I can actually do the same thing with x2. The only difference is in the derivation you're going to have to put x2 in the second column of the identity matrix, and on the right hand side you're going to substitute the second column of A with the B vector. So this is B2, and you can see immediately that x2 is the determinant of B2 divided by the determinant of A. So this is basically Cramer's rule for solving linear system of equations Ax equal to b, and you realize even if you have a trivial system of equations like 2 by 2, you're going to have to compute 3 determinants, okay? The determinant of A, so that's the matrix 3, 4, 5, 6, and then you're going to have to substitute with 2 and 4 the first column, so you get matrix B1, and the second column of A to get matrix B2. So you have to calculate 3 determinants. And for an n by n matrix, obviously you're going to have to calculate n plus 1 determinants, and that's why Cramer's rule is really not an efficient way for solving Ax equal b. Elimination that we covered earlier in the courses is the right way to actually proceed on this. So in this case, using Cramer's rule, you can derive directly what x1 is as the ratio of the 2 determinants, and you can derive this supposed to be x2 there, and you can derive x2 as being the determinant of B2 divided by the determinant of A. All right. So can we use now this idea to actually compute the inverse of a matrix And I'm going to do this for the very simple case of a 2 by 2 matrix. Okay, remember what is the inverse of a matrix, right? So A multiplies A inverse and gives you the identity. Let's concentrate on the problem of A multiplying the first column of A inverse to give you the vector 1, 0. Okay, this is the problem that I have written here. A multiplies x1, x2 to give you the vector 1, 0, and similarly A multiplies the second column of the A inverse to give you the vector 0, 1. So really what we have to do is we have to solve two linear system of equations using Cramer's rule. And you remember for each of these system of equations, you have to compute two additional determinants in addition to the determinant of A. So all the determinants that you have to compute are given here. And so you're going to have to compute the original determinant of A, which is the first matrix. Then substitute the first column of this with 1, 0, substitute the second column with 1, 0. And then for the second system of equations, substitute the first column with 0, 1, and then the second column with 0, 1. If you do this for this particular problem, you actually can compute x1, x2, y1, y2, and immediately you can see that A inverse is given by this very simple equation that looks very familiar to you. What I want you to notice is the following. So if you look so this is 1 over the determinant. Okay, that's nice. So what is D? If you look at D, it's really the cofactor corresponding to element A, because if you eliminate row 1 and column 1, you get D. Similarly, A is the cofactor of element D. If you eliminate row 2 and column 2, you get A. But let's look what minus B is. If you take let me go back. If you take the cofactor of element, so this is the element 1, 2 of the inverse matrix. So let me take the element, the element 2, 1 of A and compute the cofactor of the element 2, 1. You notice the cofactor of the element 2, 1 is minus B. So in the element here, 1, 2, I don't have the cofactor 1, 2, but I have the cofactor 2, 1. So effectively, what you have here in computing A minus transpose, you have the matrix of the transpose of the cofactors. Okay, so this is a very nice result, basically, for computing the inverse of a matrix. And let me just give you the formula in general. If you want to calculate A minus 1, is C transpose divided by the determinant of A, or if you want to calculate the ij element, is the cofactor Cji. Okay, you have to reverse the indices divided by the determinant of A. And I remind you the cofactor, let's say the cofactor here Cji would be the determinant that you compute of the matrix where you eliminate row j, you eliminate column, you eliminate row j, I'm looking at Cji here, so you eliminate row j, column I, and then you have to multiply by the sign that is minus 1 to I plus j, okay? Minus 1 to I plus j. All right, I think the next few slides basically repeat the same things for 2 by 2 and 3 by 3 determinants. So I'm going to bypass all of those and go to slide 75 to finish the lecture today by discussing a little bit about areas and volumes and convince you that areas and volumes are really determinants. So I'm going to start with the area of a triangular. So if I have a triangular with defined with these three nodes with coordinates x1, y1, x2, y2, x3, y3, you can actually show geometrically that the area of the triangular is the determinant that you see. I want to simplify this, and I'm going to simplify by taking one of the coordinates of the triangular, let's say coordinate 3, to be the center of the coordinate system, so to be the point 0, 0. So effectively, I can write this area of the triangular as 1/2 of x1, y1, x2, y2. Right? So the area of the triangular would be 1/2 x1, y1, x2, y2. Again, this is by taking one of the coordinates of the triangular to be the 0 point. If I extend this to a parallelogram, again with one of the points grounded at 0, 0, the area of this parallelogram will be twice the triangular. And there you get this beautiful formula that the area of a parallelogram is literally the determinant formed by putting the coordinates of the 2 points as the rows of this matrix that you see on the equation here. So effectively, this determinant here has the exact same meaning as the area that we're familiar with in 2 dimensions. Now, if you want to be adventurous, you can actually, without doing any algebra, you can show immediately that if you have a scenario like that with these 2 vectors x1, y1, x2, y2, you can show that the determinant formed by this matrix that you see here really satisfies all the properties of the determinant, which means, and as a reminder, remember property 1 is the determinant of the identity is equal to 1. So in our case, it would be the determinant of a square parallelogram, basically of a square, being equal to 1. That's true. Then if you exchange rows 1 and 2, that the sign of the determinant is reversed. Certainly that's the case here, but in the context of areas, we're interested in absolute value, so that doesn't matter. And then we have to show linearity on each row. So for example, if you, let me just jump directly, if you multiply one of the sides of the parallelogram by some number t, you will expect, if this is a determinant, the area to be multiplied by t. We already know this, right? So that's nice, that's the case. And then you need to show linearity on each row. And the way you do this is if you look at the parallelogram that is being formed by adding to x1, y1, x1 prime and y1 prime, you literally get the area of this dotted parallelogram, and you can show that that area is the same as the sum of a and a prime. Geometrically, you can show it because the triangular that you see on the bottom here has the same area as the triangular that you see on the top. So basically, the linearity on the properties that we expect for what we can call a determinant are satisfied by the area. And so area and determinant are basically synonymous, and you will make significant use of this in many courses, especially when you have to compute integrals and you have to integrate in space, for example. More interesting, right? So we do this problem here in 2 dimensions, but you can extend this in n dimensions, and you can talk about volumes in n dimensions. So since we said the volume, so let me see what we can say about the determinant and a volume. So if you have 3 vectors that they are not in the same plane, in principle having 3 vectors that they are independent, if you form the parallelogram, you can actually prove with the same logic that we discussed before for areas that the determinant of the matrix formed by using each of these vectors as a row to a matrix, it is actually the volume of the parallelogram. Okay, so you can actually show that if all the sides of this parallelogram are equal to 1, the volume is equal to 1. If you multiply one side by the constant t, the volume is multiplied by t. You can solve linearity and all of these nice things. So the volume is really the determinant formed by putting the three vectors as the rows of a matrix. So let's finish a little bit about discussing things we will use later related to vector products and cross products. So of course we have seen the inner product up now, but let me say a few things about the vector product. And I think this is an appropriate time to actually introduce this, simply because we're going to use, at least conceptually, the definition of determinant to write some of these vector products in an efficient manner. So what's a vector product? If you have vectors A and B, and I'm going to assume that these vectors are not parallel to each other. So the vector product is another vector. First, I'm going to have to define what its magnitude is. So the magnitude of the vector product is the magnitude of A times the magnitude of B times the sine of the angle between those two vectors. What is the direction of AB? So of A cross B. So if I go on the next slide, the direction of the cross product is perpendicular to the plane of A and B, and the orientation of the cross product vector is defined by what we call the right hand rule that I am going to indicate for you on the next slide. So if I can go directly, this is how the direction of A cross B is defined. So if you place your thumb in the direction A, then your next figure in the direction B, then the vector V should be exactly as indicated there. So again, this is a good way to see the direction of the A cross B, okay, using this right-handed vector triple that you see in the figure. Another way for me to, using again your right-hand side, is you can point all your fingers from the direction of A to the direction from A to B. Then your thumb has to be in the direction of the A cross B. Okay, and I think there is a schematic of this later in the slides related with what is referred in the literature as the right-handed screw. So if I want to show you so let me actually show you this alternative definition again of the direction V with the right-handed screw. Okay, so any way that it works for you is fine with me. Just be sure that you know how to calculate properly A cross B. Now, you may ask me again, what is the relation of all of this with determinants? And here is the answer. If you try to calculate the vector A cross B, you can actually symbolically write it as the determinant that you see here, where the first row are the unit vectors I, j, k in the directions 1, 2, and 3. This is the vector A, the components in the same coordinate system, and this is the vector B. And if you can expand this in the first row, you get the first component of A cross B, the second component, and the third component. The same way you expand in cofactors on the first row. The only difference is the first row is not numbers, but they are unit vectors. Okay, so this is a nice way to remember the determinants. In manipulating cross products, I want you to remember that the notation basically for taking cross product between unit vectors. So if you place the unit vectors in axis 1, 2, 3 clockwise, so if you have the vectors I, j, k clockwise, so if you take the inner product in a clockwise direction of two vectors, you get the third vector in a row. So if you go I, j, cross product, you get k, j, k, you get I, ki, you get j, but if you go in counterclockwise order, if you take j cross I, you get minus k. These calculations are not to be taken lightly. They're extremely essential when you work with cross products and doing this sort of algebra. So let me give you a few properties of the cross products, and we will see more as we move forward in the course. If you multiply by a scalar, you can move it from left to right, from applying it to the vector A or to applying it to the vector B, as you see in this equation. The results are the same. This cross product is distributive when it comes to vector addition. So if you have to find the cross product of A with B and C, you can write this as the cross product of A with B plus the cross product of A and C. But here is an extremely important property. The cross product is not commutative. So if you try to compute A cross B, it's not the same as B cross A. It's actually minus B cross A. So actually, the cross product is anti-commutative. Okay, this is extremely important. Remember, the dot product A dot B is the same as B dot A, but A cross B is minus B cross A. And on the picture on the right, you can see both vectors A cross B and B cross A with the correct orientation using the right hand rule that we discussed earlier. Let me also mention the following is not true. So the associative property is not valid for cross product. So if you have to calculate the cross product of A with the cross product of B and C, this is not the same as the cross product of A and B cross product with C. Okay, this is not the case. And I will give you formulas later in the course on how to compute this cross product efficiently, but literally because you already know in terms of determinants on how you compute the cross product of B and C, you should be able to compute the cross product of A with the cross product of B and C. All right, so you don't really need a formula from me on how to do this. Okay, so one more cross product before we finish. This is the scalar cross product. So before I indicated A cross product with B cross C. So now what I have is I have a cross product of B and C, and then I have this thing dotted with A. This obviously is a scalar because B cross C is a vector. Dotted with another vector, you get a scalar. And has a very nice geometric interpretation, has a very nice way to calculate it. So if you actually assume the three vectors A, B, C to form to be the rows of a matrix, you can show, and I can go directly to slide 96, you can actually show that A dot with B cross C is the determinant of this nice matrix that you see in this equation. So again, the determinants are very handy to compute this scalar cross product, as we call it. And of course, if you remember, we already have seen that this determinant is really the volume of a parallelogram with sides that are defined by the vectors A, B, and C. So you maybe wonder, where is this? So now we're stating effectively, if this formula is correct, right, we're stating that A dot B cross C is really the volume of the parallelogram formed by B, C, and A. And I am going to show you this geometrically. Actually, I'm going to jump a little bit, and then I'm going to come back. I'm going to show you this. If you look at this parallelogram, right? So you see in the picture B cross C, okay? And then we have A dot with B cross C. So if you look at the volume of the parallelogram, what is the volume? Is the height h times the area formed by the vectors B and C. and the height h is really nothing else but the magnitude of A times the cosine of the angle between A and B cross C. Okay, so but we already have seen that the area of the parallelogram is really the magnitude of B cross C. So effectively, you can see that this dot product between A and B cross C is nothing else but the volume of this parallelogram. Okay, so there is a geometric interpretation, and because this is a volume, right? You can actually pose lots of interesting theorems here, and for example, you can immediately see that when you compute the volume, right, you can use one side of the parallelogram defined by vectors B and C, but you can use another side defined by the vectors A and B. Okay, so you anticipate that A dotted with B cross C should be the same as A cross B dotted with C, and that's indeed the case. And also, because here we're talking about volumes and determinants, effectively you can pose the linear independence between the vectors A, B, and C as when the volume of the parallelepiped that is formed by these three vectors is non-zero, right? So if you get a non-zero determinant and non-zero volume, you can say that the three vectors are independent. Again, the proof here are rather trivial, and they're being discussed in the slides for those who want to read a little more, but there's really nothing there beyond the things that we discuss. Okay, so let me see if there is anything to summarize here. So there were many new ideas, right? We discussed about Cramer's rule for computing AX equal to B, and then also Cramer's rule for computing the inverse of a matrix A, and for computing the solution to AX equal B, we had to compute these matrices B1 to Bn, where we take the matrix A and we actually substitute each column one at a time with the vector B. So we had to calculate n plus 1 determinants. Okay, we postulated, we show it actually, we prove it literally on how you compute A inverse as C transpose divided by the determinant of A. And literally to prove too, we use Cramer's rule for solving AX equal B. We discuss about volumes and areas as being determinants, okay, and then we finish actually talking about the vector product and the scalar cross product that we affiliated with volumes of parallelepipeds in 3 dimensions. All right, so we are finished more or less with determinants. And the most significant use of determinants, it will start coming up in the next lecture when we discuss about eigenvalues and eigenvectors. So until then, this is the end of lecture 16. See you next time. Bye.